Floor is yours. No, I think they should be able to hear you. Yes, they're recording.
We good to go?
You're good to go, yes.
Good morning, all. I'm Midshipman Camden Berry. I'm Midshipman Jacob Schultz.
I'm Midshipman Hyan Lee.
I'm Midshipman Carl Kruger. And we are Propulsion Pioneers, and we will be presenting design for an LPG tanker that travels between Long Beach, California and the Hawaiian Islands. So a brief overview of the topics that will be covered in this presentation include the main engine, the fuel oil system, lube oil system, air supply system, and control budget system. The engine specifications that we selected were the MAN 7G60ME LGIP main engine. It is a engine that has a max RPM of 103, an acquisition cost of $51 million, a yearly lube oil cost of $1.3 million. The 100% rated load is 19,980 kilowatts. It is a direct drive, slow speed, 2-stroke diesel engine that is equipped with 2 TCT 50 ML MAN turbochargers. The full load of the main engine is 19,980 kilowatts at 103 RPM, and the C margin accounts for 98 RPM at 16,898 kilowatts. If you trace the dark blue line on the load diagram there to the power rating provided by the manufacturer, it will display the RPM that moves. Some load considerations include the power takeoff device that the electrical group will discuss. It takes 3,000 kilowatts of load, and the waste heat boiler system will add an additional 1,000 kilowatts of load. Okay, in comparing our LPG engine with other engines, we looked at the Wärtsilä and Kawasaki variants of the LPG engines, but we ended up ultimately going with the MAN BMW variant. Some reasons, all these engines can run MGO and LPG, but this engine in particular is also capable of running VLSFO, which we want to utilize in case the scenario happened where we had to use that fuel and that was available. Another factor we considered is MAN Services provides year-round servicing on every continent for these engines, and there's specifically a servicing port in San Diego, California, not far from Long Beach, which could be utilized if this engine had maintenance issues that needed to be fixed. And another thing we looked at was this engine has a very high reliability rating. About 170 of these engines have been bought since 2018, showing the shift to LPG, and more of these engines are being bought from MAN BMW. Looking at emissions with LPG and this engine, according to this 40 CFR Part 143, with the acts to prevent pollution from ships, we are complying with MARPOL Annex 4. And looking at IMO Tier 3 for the North American emission control for the Hawaiian Islands and Pacific Coast, this tier is focused on reducing nitrogen oxide emissions into the environment. So with this engine, using LPG is better because there's a lower sulfur content and lower CO2 emissions. So using this engine with LPG, we're able to have reductions in LPG emissions. Nitrogen oxides upwards of 20%. Sulfur oxides around 97% reductions. Carbon dioxide upwards of 20%, and particulate matter upwards of 90% reductions. Just some basic dimensioning of our engine. We have it at 30.3 feet across and about 53 feet high.
All right. Next up is the lube oil system for the main engine. This is the main lube oil system. As seen here, there is the lube oil sump tank. Taking suction from this will be the main lube oil pumps. And the oil will then move to the main lube oil cooler system, through the filter system, and to the main engine. The main lube oil pumps and cooler will be talked about next. Looking on to the main lube oil pumps, some key features of this pump is the 90 kilowatts and 125 horsepower provided by the WEG W22 electric AC pump combined with a positive displacement rotary pump. You will be using a 460 volt voltage from our electrical group with a capacity of 13,000 cubic feet an hour and a discharge pressure of 60 psi. Lube oil will then move from the pumps to the lube oil cooler, as seen here. lube oil will enter at 122 degrees Fahrenheit and exit the plate type heat exchanger at 113 degrees Fahrenheit. This is a plate type heat exchanger using low temperature fresh water from the cooling group, and will be using 97 degrees Fahrenheit in and 106 degrees Fahrenheit out of water. This will have the same lube oil capacity of 13,000 cubic feet an hour as the main lube oil pumps. Next up is the turbocharger lube oil system. Key features of this will be the turbocharger lube oil tank, which is sloped. It will then be taking suction from the turbocharger lube oil pumps, ran through the lube oil cooler, and once again to the filter unit and to the main engine turbochargers. Key features of this is the turbocharger combined filter unit, which will again remove any sediment or matter that may be stuck in the tank. Looking at the turbocharger lube oil pumps, this will also be a white design, just smaller than the main engine. It will use a 3.7 kilowatt, 5 horsepower motor. It will once again use a voltage of 460 volts with a capacity of 17.5 cubic feet an hour at 60 psi discharge pressure. Next up will be the lube oil purification system. Taking suction from the bottom tank and sump, the lube oil separator pump will take suction and move the lube oil through the preheater into the main engine purifier. Additionally, the lube oil storage tanks as seen above will then provide lube oil to the purifier, which will be gone through this diagram right here, through the line, through the filter, and to the separator back end. This will be talked about next, some of the smaller units. The purifier is an alpha Laval purifier. It will be using a 3.7 kilowatt or 5 horsepower motor to power the purifier. It has a capacity rated at 95 cubic feet per hour at a rated temperature of 194 degrees Fahrenheit. In order to provide the 194 degrees Fahrenheit to the purifier, a Elborg EHU shell and tube type preheater will be used using 70 kilowatts of electrical power to preheat this lube oil from 113 degrees Fahrenheit to 194 degrees Fahrenheit per the alpha Laval specifications. In order to move that lube oil from the sump to the purifier, a separator pump will be used. This again is a WEG series motor with 5 kilowatts of power and 6.7 horsepower. It is a positive displacement rotary pump. It will have a rated pressure of 60 psi, a capacity of 95 cubic feet an hour. And once as seen here is the separator pump filter, which will remove any sludge, anything before going through the pump into the purifier. Next up is the cylinder lube oil system to the cylinder liner. This is a MAN Category 2 cylinder oil system provided by the manufacturer. This will use lube oil that will be, cylinder oil that will be provided in the next slide to combine with the cylinder in order to provide proper lubrication. This will be a 18.5 to 21.9 temperature dose of cylinder oil with a base number of 40. All lube oil systems prior to this, and including this one, are 46 CFR 655. Taking a closer look into the mixing oil system for the cylinder oil, we have a low BN cylinder oil service tank and a high BN cylinder oil tank, which is the base number. This will be entered into the smaller, as seen here, low base number oil tank and high base oil number tank, which will be then provide the adequate amount of mixing oil to the mixing tank, which based on later you'll see in the fuel presentation is the primary and secondary modes. This will allow the engine to use the proper base number based on fuel type, emission type, or anything else the engine.
The construction of the LGIP engine is similar to that of a conventional slow-speed diesel engine. As a result, there have been manufacturers that have been easily able to retrofit and integrate the LPD system to the existing diesel engines. The LPD system consists of the fuel valve train, ventilation and leakage detection, electronic window valve, electronic gas injection valve, and the fuel booster engine. The fuel valve train is located below deck and outside the engine room and is broken into two parts, the supply valve train and the return valve train. The supply valve train supplies LPG from the low flash point fuel supply system to the main engine, while the return valve train recirculates the LPG from the main engine back to the tank. Once the engine is secured, the supply valve train and the return valve train are both purged with nitrogen. An important feature of the fuel valve train is the double block and bleed valve function, which is highlighted in the diagram to the right. Under the International Code for Construction and Equipment of Ships carrying liquefied gases in bulk, specifically 16.26, states that all gas utilizing unit must have a set of 3 automatic valves, 2 of which are the block valves, which will restrict the flow in the lines, and the third one is the bleed valve, which will allow the line to ventilate to the knockout drum and outside the engine. This is beneficial for any safety purposes and maintenance. All pipes carrying LPG will be double wall pipes. This complies with IGC 16.21, which states that any gas fuel supply must have a double wall piping system with the gas flowing in the inner pipe and ventilation air flowing in the outer pipe. To detect leaks, hydrocarbon sensors are installed in the double piping system. This complies with 46 CFR 154.706, which requires a continuous detection for leaks. In the event that a gas leak is detected, the supply valve train will be secured and the fuel valve train will change over to MU. This complies with IGC 16.22, which states that when a gas leak is detected, the supply valve should be secured and should not operate until the gas leak has been found and repaired. To the right is a cutout view of the fuel booster injection valve, which combines the fuel booster and the fuel injector into one unit. Basic operation, the LPG is supplied at 725 psi, following the channels highlighted in yellow, and will fill the booster chamber. Once the booster chamber is filled with LPG, the electronic window valve will be activated and allow hydraulic oil to flow to the top of the plunger. The LPG will then flow in through the internal holes near the injection. Once the LPG is pressurized to 8,700 psi, the control oil pressurized at 4,350 psi will activate the electronic gas injection valve, and once the ejection valve is activated, the cutoff shaft is pushed up and the LPG is injected into the combustion chamber. Lastly, sealing oil at 1,160 psi prevents LPG from leaking into the hydraulic oil. The main engine will operate in dual fuel. In the primary mode, LPG is used with MDO as the pilot fuel. About 10% of the pilot fuel is injected when engine modes are below 10%. As the engine mode increases, the pilot fuel will decrease to about 5%. At 85% MCR, the specific pilot oil consumption is 9.1 grams per kilowatt hour, and specific gas consumption is about 141.2 grams per kilowatt hour. Since LPG is a mixture of liquid propane and butane, it has close to 0 sulfur emissions and lower carbon dioxide emissions than compared to MDO. A round trip operating in the primary mode will cost about $306,000. When operating the secondary mode, MDO is the primary fuel and the LPG system is secured. At 85% MCR, the specific fuel oil consumption is 161.2 grams per kilowatt hour. And operating the secondary mode, the cost would be around $658,000 round trip. Therefore, operating the primary mode is more costly.
Looking at the starting air system for our main engine, we had 2 Ring-Sauer-Levant 3-stage reciprocating air-cooled compressors. These 2 compressors supply the compressed air for 2 main air reservoirs, each size at 141 cubic feet, holding the compressed air at 435 psi at 212 degrees Fahrenheit. We also have an emergency air reservoir capable of holding 7 cubic feet at 116 psi. And for this starting air requirements for this engine, since it is a direct drive engine with a controllable pitch propeller, there are only 6 consecutive starts required to meet the air capacity to start the main engine. This complies with 46 CFR 112. Right here at the bottom left, we have our air compressors that pass through check valves to our oily water separator, which removes the condensate and oil from the compressed air to the oily bilge. This air passes to one of the 2 air receivers. There are relief valves on top of these air receivers to relieve pressure above 435 psi, and there are drain valves at the bottom to remove any condensate in the air receivers. And from these air receivers, the air compressed air is passed to our reduction station through a 40 micrometer filter to adjust the air fuel mixture to prevent airlock when the air reaches the push on those pistons and cylinders. Looking at the compressors more deeply, these compressors are reciprocating air cooled, providing compressed air for 435 psi to the main engine. They have a max output of 580 psi, 3 stages, 3 cylinders, maximum speed of 1780 RPM, maximum charging capacity of 9,358 cubic feet per hour, and power consumption of about 60 kilowatts. For the oil air piping components, oil water separator, we have right after the compressor for the air receiver to remove that condensated oil. During the air receiver, we pass through an actuated ball valve to a non-return valve to a solenoid valve to our main air starting valve to let the air into the cylinders. Calculating the size of these air receivers, each one is calculated to be needed at about a capacity of 240 cubic feet. And these with two receivers, we have around 280 to adjust for that. The scavenger air system itself consists of 2 TCT 50 ml MAN turbochargers, as well as 2 auxiliary blowers. The auxiliary blowers themselves will start as the engine is going through 25 to 35% of its engine load from rest, and then it will additionally also remain when it is going down from 40 to 30. If it's not in a rest condition and it's just operating at a load between 30 to 35%, it will operate. And these blowers are variable, and so they will increase or decrease their load to compensate for the pressure. The turbochargers themselves have an efficiency rating of 80%, which is a reason that we selected them. There's also a turbocharger sizing diagram for the turbochargers that we selected. We chose 2 of the TCT 50s, not only because the weight of 2 of them is less, but the efficiency of the turbochargers themselves are better when it's not operating at its maximum capacity all the time. It's easier on the mechanical functions of the turbochargers themselves. And then the sizing diagram is on the way there. The control logic system for the vessel utilizes 2 cores. One is the MEECS core, and the other is the SF supply control system. This is more of an operating control system that functions on the actual maneuvering of the plant versus, as people state later, their Kongsberg automation system detects alarms and monitors. But this actually controls the injection functions of the plant, such as the fuel oil injection, starting air injections, cylinder lube oil, those functions. The calculations that we we calculated fuel by multiplying the specific fuel consumption by the kilowatt load of the plant, by the amount of hours in a round trip, and then with the ratio of LPG to diesel oil, the power rating, and then we converted the grams to pounds. We took the pound cost from the IMARC website, and then we converted it to the cost per round trip required for fuel. The calculations that we got for acquisition as well as lube oil costs were taken from the economic comparison of various marine power plants by Jose Mina. In conclusion, what we presented is the BMW main engine for LPG. What we've gone over is engine specifications, lube oil, fuel oil, starting air scavenger, and control logic for this engine with LPG ammonia tanker from Long Beach to Hawaii. Thank you.
All right, guys, terrific. All right, start with questions from the live audience. Professor Rolls.
Your turbocharger, you used an E-lock for lubrication. Is that E-lock at various speeds so to accommodate different power states?
What do you mean E-lock?
Electric oil pump. Your diagram shows as a motor.
Yeah.
Motor driven oil pump. Does that vary with the loads on the engine?
You mean like the speed of the RPM, like a turbocharger?
Yes, yeah, the control logic system itself, that I outlined, it's monitored in CS core, that's one of the functions.
So the VFD, okay.
Yeah.
All right. The second question I have is they had an electric shell and tube preheater for the purifier. As opposed to using waste heat or anything else, they have to reduce carbon emissions or anything. Had that be considered?
I did not consider that. I used what was easiest for the purifier and based off of valve recommendation.
All right, Professor Gardner.
I thought this was a great start to the Capstone. And my comment, I don't really have any questions. I really just have comments. I mean, I think they're pretty minor, but I haven't had the benefit of the read aheads, which I appreciate. It seemed to span across all the projects. So, one thing, I saw the flow on pumps was given in cubic feet per hour, very unusual. That would be converted into gallons per minute. Couple of minor workmanship issues on the drawings. So the all caps on the fonts is traditional for a mechanical drawing. Used on the drawings used to be a PXD font, which is really outdated. I would go with Roman S and keep everything consistent with PDFs. I saw that the horsepower on the separate, first pump I saw was a 5 horsepower motor. Good, it's the size of the motor. Then I saw a 6.7 horsepower pump, the motor on the separator. That's unusual. You would round up to the next standard size, the motor, which would be a 7.5 horsepower. And these are engineering, these are becoming engineering drawings. So you really want to include all the detail. And as a couple examples of gas heat exchangers, there's typically going to be vents and drains. And also if there's a heat source, some of these heat exchangers are considered unfired pressure vessels. A lot of times there's a little 3/4 inch relief valve just to burp out any build up of the fluid pressure if somebody mislines the heat source. Like the air receiver, I would almost expect to see like an automatic drain. And the last thing I'm going to say, the last thing I'm going to do is actually ask a favor. That when you're done, maybe take that controls book that you have and just read chapter 17, which goes through SCADA controls and automation and how to present engineering drawings. Because it looked like there were only temperature and pressure indicators, but I'm pretty sure you probably have an automation system that's communicating with something.
If I may interject, yeah, some of the drawings such as these are taken from the drawings that I was able to complete last saved. Working with Professor Sephora, we had a lot of technical issues. So I wasn't able to make a lot of the final edits I was hoping to, as my AutoCAD literally got deleted. So
Yeah, I know. I gave some feedback.
Yeah, absolutely.
Yeah.
So yeah, take it considered, but I just wanted to make that known. So yeah, thank
I
you.
appreciate it. Chapter 17.
Professor Gardner, by the way, was the Capstone Marine Engineering Systems Capstone supervisor for how many years?
Professor Assembler, I think they're equal.
Okay, so you're getting a compliment from somebody who's
Thank you, sir.
Professor Assembler.
Also, compliment you because you had a number of systems. I know in the past, sometimes the main engine group, there was a separate group did the lube oil system and a separate group did the fuel oil. So you did all of it. And now I've been involved in this project pretty much every year since 1992. So I think you did it good. And the other thing I want to point out, your presentation was very well. Went very well. So everybody participated. You weren't reading off cue cards. Very good. Couple of comments. I was also going to comment about the choice of cubic feet per hour used for the pump valve. And I saw that really throughout most of the projects, which is Professor Gardner has already commented on, is unusual. Generally, for pumps, if it's the SI units, they usually use cubic meters per hour, but for USCS units, it's typically gallons per minute. Following up on it, what type of rotary pumps did you select?
I think there are those vein pumps, I believe.
What do you mean the same pump?
Vein pump.
Oh, vein pump, I'm sorry, I didn't hear you, okay. And what are they? It probably would have been good to provide some additional information on those, maybe performance information, or at least what type. So, those horizontal or vertical pumps?
Yeah, so the pump would be vertical, so they would be moving horizontally. Like,
Okay, so.
yeah, horizontal,
Okay,
or
all right.
vertical shaft, horizontal.
All right, good, but yeah, it would have been good just to clarify that,
Sure.
okay. One other thing, the horsepowers that you selected, if I look at, for example, the turbocharger pump. That, which was 17.5 cubic feet per hour, I believe.
Yes, sir.
So that equates to about just a little bit over 2 gallons per minute. So if I look at that with a 60 PSI pressure, that comes out to like, about less than 1 horsepower. But I think you have a 5 horsepower motor. So my question is, how did you select the motor sizes to go with those pumps?
Sure, yeah, so based on the main engine document, the manual that we had, a lot of this was also in liters, cubic meters per hour. So I just did a quick calculation in order to allow it to convert it, and then kind of take again some of the consideration, vein pump and other things like maybe losses and such.
Okay, all right. Yeah, 4.403, you multiply cubic feet per hour times that number, you'll get gallons per minute. All right, other than that, one other thing, I think on your slide where you refer to Annex 4, I think you really meant Annex 6.
Okay,
But other than that, those are minor comments. In general, I'd say you did an excellent job. Thank you.
Great. Stephen?
Nicely done. Good start for Capstone too. I agree. Just a few comments and maybe one question. When you were talking about the engine emissions on slide 6, it would have been nice to actually see the values that you're supposed to move rather than just percentages.
it is a reduction like with the LPG instead of.
Right, but I would have liked to have seen what the CFR actually says for the table on what your engine RPM has to mean. That would have been better to have seen that. Slide 17, I think, where you had the cylinder oil, would have been nice to see some flow arrows in there. And then, yeah, see, it's just a bunch of lines. There's no flow arrows on it. And then slide 21, where it's talking about ventilation and things like this. We made a reference to the IGC code, which is good. But you're also hauling that fuel, so you also have to reference IDF. So that trips people up sometimes. You have to check both books to make sure, especially as tankers. I'm not only am I hauling that, but I'm also using it. So you have to touch on both of those. And you'll have to do, anytime you have gas as a fuel, class will make you do a hazard review of all of the systems in the engine. From where am I venting this fuel? How am I detecting fuel leaks? To what ATEX or IECEX ratings that I have on my equipment. They're going to want to see all of that stuff. So it would just been nice to see if you had any equipment that needs ATEX or things like that and what the zones are. And then the only other question I had was, assuming this has to get built in the US, does the shipyard have a license to build that?
I'm not sure the shipyard aspects I could get back to.
Yeah, they don't pick the shipyard. They just work on the design. So yeah, that's yesterday's group. All right, I think we'll go to the Zoom audience. Joe, you unmute yourself. Let's see how this goes.
Did it work?
All right,
Can
Joe,
you hear me?
Joe, hold on 1 second. I think I got to turn the volume up here.
Can you hear me now?
Yes, we can hear you now.
Oh, good. Okay, excellent presentation, guys. I'm very pleased to see that you really took a full spectrum on the propulsion engine. Three questions. First one is, since you're going to be using LPG as a fuel, is there any purge provision before starting that engine with gas? In other words, the use of gaseous fuels is kind of a new thing to the world of propulsion diesels. And there have been problems with exhaust, basically the flue gas path having pockets of gas in there. So did the engine manufacturer talk about this at all to you, or did they show any literature? But usually we're starting to worry about actually putting in either a time delay on start where you can crank the engine long enough to purge the exhaust path, or using a purge fan. So was any of that mentioned by man or no? I can't hear you guys.
All right, sorry about that. Yeah.
You mentioned it with the supply valve train and the return valve train being purged, upon when the engine will be secured, but they'll also have the nitrogen go through.
Okay.
At the beginning to make sure that there are no leaks before starting the engine.
Okay. Second question I had is on lube oil. Gas-fueled engines, one concern for lube oil, and then diesel, whole different concern. Did man give any guidance about lube oil? The manufacturers have been shying away from this until there's enough experience to know what really works. Usually they just say use a synthetic oil, but they won't give you a spec. Did you see any kind of spec info for lube oil?
Yeah, absolutely. So part of the project manual by man, they use a SAE 30 type oil. That oil was also combined with the cylinder lube oil, as the cylinder lube oil had a higher base number. That would allow it to coincide with the actual main engine lube oil, not allow for corrosion, and we'll just work together very nicely based on the answer to that.
Okay. And my last question is on the start air system. I didn't see any automatic drain traps on the oil separator or on the starting air receiver. You might want to consider just as a rather important item.
Yeah, I know I had
That's
the
all I got.
manual receivers, but I will look into automatic.
All right. Thank you, guys. Excellent presentation.
Thanks, sir.
All right, Mr. Cooper.
Hey, good morning. I have two items. Your lube oil pumps, I saw there was in the details for it that they were 460 volts. But looking at the electrical system presentation, they have a 480 volt bus. Was there any discussion on how how a 460 volt system would be powered?
Yeah, so I think I was working with the electrical group and we were discussing what voltage we were gonna use. There might have been a mix up whether it was 460 or 480. I remember I provided them with the voltage, at least for 460, so I'm not sure that.
Yeah, 460 is kind of unusual, especially for US ships. I would expect 480. As a second item, did you have a minimum lube oil temperature requirement
I'm sorry,
from the
say that
engine?
again?
Did you have a minimum lube oil temperature requirement?
So at least
So I
recommended
go ahead.
specification. It would like it at 113 degrees Fahrenheit, with adjustments in the regulating valve for the water to the plate tank heater. That had a set point of 113 degrees Fahrenheit, so I'd say maybe plus or minus 5 degrees, maybe a little bit more.
Okay, so those plate type, were they just coolers or were they also heaters?
They're just coolers.
Okay, so how would you, what provisions would you have for starting your main engine after coming out of a shipyard in Seattle, for instance, in the middle of winter, where the water temperature is 40 degrees or 50 degrees? and you've been there for a couple months.
Sure, I believe I might have talked about that a little bit more in the actual project. Obviously, since there was a lot of lube oil operations, I don't think I was able to get into the actual preheating of the engine. If you're saying something like a cold start.
Yeah.
So I could definitely talk about that more as I answered your question.
Okay. Yeah. I would have thought to have seen heaters in the system as well as coolers. So that's all I have. Thank you very much.
All right, thank you, Eric. All right, Brock, give me 1 second. I'm gonna see if I can eliminate this feedback here. Let me just try one thing real quick.
Yeah, no problem. Take your time.
All right, Brock. Oh, Jesus. All right, never mind. It didn't help.
I think it got worse.
All right, let's try again. Yeah,
right.
still got it. Brock, go ahead.
Okay. Yeah, great presentation, guys. Appreciate the hard work you guys did on that. There's a lot of systems to cover, as everyone said. So, yeah, just a couple of things. So I focus on the regulatory side. My big question, and it's not just for you, it's for everybody, is if this vessel is being built to the CFR standards, or if it's going to be, at the end of the day, built under the alternate compliance program. So just to keep that in mind, that changes your regulation regime a little bit. So not just you guys, but everybody. So that was just my comment overall. But other than that, Professor Sembler touched on the Marpol Annex 6 versus 4, so make sure you change that. And then the only other comment I had was the fuel consumption slide deck. You could go to that for just a minute. If not, that's okay. Okay. Yeah, so I would say the units on fuel consumption are a little too granular for my relatability. Maybe like tons per day or something that we can like kind of quantitatively measure a little bit. Something a little bigger than grams per kilowatt hour would be, I think, more useful to somebody looking at some of these things. But maybe you could do both. But I think it's a little too granular. But maybe that's just my personal preference. So, but other than that, the IA. So another thing with the emissions side is you guys had mentioned 40 CFR 143, which is good. There's a section in there you might want to take a look at if they are required to get an engine IAPP certificate from the EPA. And I'll drop it in the comments in the evaluation form. But if the engine meets some specific requirements, it's not required. So just something to think about on the emission side for you guys. Just look at the CFR site and then the annex. But other than that, that's kind of all I had. But great presentation, guys. Appreciate it.
All right, thank you, Brock. All right, we're ready to move on to the next group. We have a 5-minute break. If anybody wants, we've got water, we've got snacks outside. And the next group will be up in a couple of minutes and see if we can work on clearing up this feedback here. All right, thanks. Be back in 5 minutes.